Hi everyone. I hope you are fine. So today I am going to explain to you about linear multi-step method. So this is a numerical method for ordinary differential equation. Linear multi-step method use several values of function and its derivatives from the previous step. The standard form of linear k-step method is defined by, we have yn equals to a1 yn minus 1 plus a2 equals to yn minus 2 plus ak yn minus k, plus h b naught fn plus b1 fn minus 1 plus up to bkf n minus k. Okay, so what this means, we have the derivatives where our fi is denoted by f of xi yi. Okay, and obviously for I equals to 1, starting from I equals to n to n minus 1 up to n minus k, and we must also make sure that a squared k plus b squared k not equals to 0. Okay, so this method is explicit if my b naught here equals to 0, meaning I don't have b naught here, b naught equals to 0, and implicit if b naught not equals to 0. Okay, so this is the form of a linear k-step method. Now, why you say this is k-step? RK method is one step, but linear multi-step method is k-step because we have this number line here. So RK method that you usually want to solve, you start with yn minus 1, xn minus 1, yn minus 1, up to here xn yn. Okay, so this is RK method, one step RK method. You can obviously you have a big Y to get to yn. Okay, so from here to here, what we have here is your step size h. Right now, linear multi-step method, you can have xn minus 2 yn minus 2. This is two-step method, and you can also go up to xn minus k yn minus k. Okay, so I would say that the length from here to here will be k times h. Okay, so to solve an ordinary differential equation such as y prime equals to f of xy, okay, we can use two methods. Here we can use two methods. So they can be RK methods, and also linear multi-step method. This one. Okay, linear multi-step methods. So RK method uses one step from xn minus 1 to xn, where you obtain your yn here with the step size h. Now linear multistep method, you can have up to k step. Okay, 2 step will be from xn minus 2 yn yn minus 2 here. Okay, yn minus 2 xn minus 2, where you get 2 step to get to yn. So example of one step linear multistep method. Okay, so so let's look at k equals to 1, which is our one step method. Okay, so k equals to 1, which is our one step method. So what happened when k equals to 1? Look at this standard equation here. We have yn equals to a1 yn minus 1. That's it. For when k is 1, we have a1 yn minus 1. So I have this equation and this equation, and then plus when k is 1, I have b1. So I have these two equations. Okay, so let's write it down. So you have yn equals to a1 yn minus 1 plus h b naught y, what did they say, b naught fn plus b1 fn minus 1, b naught fn plus b1 fn minus 1. Okay, so this is for k equals to 1. Now we can derive two methods here. We can derive two methods for k equals to 1. The first method that we want to derive will be my explicit method. Now I've told you to derive explicit method, my b naught must be equals to 0. Okay, meaning I don't have this term here. So if I don't have this term here, what would I have? I will have yn equals to a1 yn minus 1 plus h b1 fn minus 1. Okay, now we can decide what is the choice of a1 and b1 can be. So you can let, if you let a1 equals to b1 equals to 1, what happened? I have yn equals to yn minus 1, a1 is 1, plus h, b1 is 1, fn minus 1. Now this method I can write as yn minus 1 plus h, f of xn minus 1 yn minus 1. So this is my explicit Euler method. Okay, now another example of k equals to 1 method is the implicit method. Okay, implicit method you can obtain when your b naught is not equals to 0, meaning I have to consider b naught now. Okay, so let's write it down. Okay, when b naught is not 0, what I have here, I have yn equals to a1 yn minus 1 plus h b naught fn plus b1 fn minus 1. This is a function of f. Okay, so let me just take a note here. I want you to remember that fn is also similar with f of x and yn. F n minus 1 meaning f of xn minus 1 yn minus 1. Okay, this is the way to write it. Now what choice of A and B that you can use to get to an explicit method. So we can say that let A1 equals to 1 and B0 equals to B1 equals to half. So we have yn equals to yn minus 1 plus h over 2, half and half, factor it out. I have fn plus fn minus 1. Okay, or I can write it as yn equals to yn minus 1 plus h over 2, writing fn minus 1 first. So I have f xn minus 1 yn minus 1 plus f of xn yn. So this method is implicit trapezoidal rule. So not all RK method you can write as one-step method, but these are some of them. Okay, so you can derive methods based on that standard linear multi-step method that I showed you just now. Okay, now the other thing I want to say that, so in this example I've given you the explicit choice and implicit choice of one-step method. Okay, now how you can find a two-step method? Okay, two-step method happens when k is 2, right? When k equals to 2. Okay, let's look at this equation again. So what you have here, when k is 2, so I can have, I'm going to use red pen here, so this n minus 1, n minus 2 when k is 2, okay, up to here, and then plus h when k is 2. I have b0, b1 and b2, fn minus 2. Okay, so you can write it down. Okay, you can write it down. So I have yn equals to a1 yn minus 1 plus a2 yn minus 2 plus h b0 fn plus b1 fn minus 1 plus b2 fn minus 2. Okay, this is the general form you can get for two-step method. Okay, so two-step method can be complicated because we wanna find the choice of the method. So one example of choice of the method is, this is people already done it. It's not you cannot simply find the variable. I'm showing you some of the variable that people have find it. So we have this method called two-step Adams-Bashford method. Okay, so how you obtain, so this two-step Adams-Bashford given by yn equals to yn minus 1 plus h over 2 3 fn minus 1 plus minus, not plus, minus f n minus 2. So by comparison, what I can see here, a1 is 1 and then a2 is 0. Okay, and then what about b0 is 0. Okay, so we know this is explicit method, and then b1 is 3 over 2 and b2 is negative 1 over 2. Okay, so you can get a two-step method which is called Adam-Bashford method, and obviously there is a way to determine this. Okay, you're not getting it, I'm just showing you what are the choice, but to get that you need to know order condition for linear multi-step method. Okay, how an equation is, the coefficient is derived is based on the order condition. Okay, so if let me just go through the order condition. I'm not going to show you the derivation of the order condition. Okay, so the order condition for order 1 will start with like this: a1 plus a2 plus a3 plus ak equals to 1. Okay, for the method to get order 1, we have a1 plus 2a2 plus 3a3 plus kak equals to b0 plus b1 plus b2 plus up to bk. To get order 2, we have a1 plus 2 squared a2 plus 3 squared a3 plus k squared ak equals to 2 times b0 plus 2b2 plus 3b3 plus up to kbk. Okay, I'm just going to show you up to order 2, so the rest of this you can find it on my slides. So the rest of this meaning, if I have order p, so what is order p meant? The order p will be a1 plus 2 to the power of p a2 plus 3 to the power p a3 plus k to the power p ak equals to 4. Okay, 4 b1 plus 2 to the power of p minus 1 b2 plus 3 to the power of p minus 1 b3 plus this is can get a bit complicated. That's why I will show you the most important one, and then the rest you refer to my slide. So this is for order P. Now when this is useful, so let me just tell you when you use this order condition. So if you have an order 3 method, for example, okay, you have order 3 method. So to satisfy the order condition, we know that let's focus on the explicit. Okay, explicit order 3. So we know that b0 will be 0 for explicit method. So the order condition, okay, we can see p is, this is p, order is p is 3, right? Okay, so when p is 3, so what we have here will be a1 plus a2 equals to 1. Okay, that's the first condition we have. So look at this one. So a1 plus a2 equals to 1, and then we have a1 plus 2a2 equals to, this is 0, b1 plus b2. Okay, so the next condition will be a1 plus 2a2 equals to b1 plus b2. Okay, and then we can have A1 plus 4 A2 equals to, that's it. Okay, so we have 2B1 okay, and then we have B2. Okay, there should be a B2 here, so I missed out my B1 and B2. So I have B0, I should have B1, and then this should be 2B2. Okay, so we have, let me just check again. So B1 for order 2, so just fix this first before I write it out. So for odd, just now it should be B1 plus 2B2 plus 3B3. Okay, not B0 anymore. Okay, so I have these two terms here. So 2B1 plus 4B2. 2B1 plus 4B2. Okay, and then I can also have, because it's up to order 3, right? So A1 plus 8A2, 2 to the power of 3, 8. And this one equals to 3 minus 1. What do you have? 3 minus 1 is 2 to the power of 2, 4 times 4. So I have 4B1 plus 2 to the power 3 minus 1 is 2, 4. 4 times 4 plus 16 B2. Okay, so 4B1 plus 2 to the power of 3 is 8. So maybe this is so this is correct. So what we have here should be, okay, it's not quite correct here. So what happened here, if I am writing another one, order 3, I should have A1 plus 2 to the power 3A2 plus 3 to the power 3A3 plus k to the power 3ak equals to 3 B1 plus 4B2 plus 9B3 plus k squared bk. Okay, if you get that, so plus 9B3 plus k squared bk. So this one is not 4. You can see the number is k. Okay, so start with 1, 2, 3, and then 4 up to I would say up to p here, up to p. Okay, so for order 3 I have this 2, and there you go. So 3B1 plus 4B2. 3B1 for 4 times 3 is 12. 12B2. Let's check it. 4 times 3, so you have 12B2. Okay, so this is for how you check the condition for order 3. How many condition you have? 1, 2, 3, 4. 4 condition. Okay, 4 condition if you want to check for order 3. So how can you find the constant here? So people, many researchers have done it with the several choice of if you look at A1 equals to -4, A2 equals to 5, B1 equals to 4, and B2 equals to 2. Okay, with this choice you can get two-step method of order 3. 5 yn minus 2 plus h f of n minus 1 plus 2 f of n minus 2. Okay, you can have this is for k equals to 2, the two-step explicit method of order 3. Okay, and if you want to have method for order 4, you need to satisfy 6 condition. Okay, this is 1, 2, 3, 4 condition for order 3. For order 4 you will have 6 condition. Okay, so what can I still say about it? So you can also have a 3-step method, a 4-step method, and so on. The methods are derived by some mathematician, and what we do now, we are just using the method. Now what is Adam? This is Adam Bashford. Adam Bashford, the difference between two types of method that you learn, it will be Adam Bashford and Adam Moulton. Okay, so explicit Adams method. So we have explicit Adams method, we call Adams Bashford, while the implicit Adams method we have Adams Moulton. Okay, so back to the general linear multistep method. The explicit one we obtain when b0 equals to 0, and the implicit one we obtain when our b0 is not equals to 0. So there are some families of linear multistep method that you can consider. And the other important term also is the stability. So we're not going to look at stability so much because like I said, the method can get a bit complicated with the derivation and so on. So this is few choices that I've shown you for using linear multistep method. So ask me any question if you have, and then I will share more information to you. Okay, that's all for today. Thank you.